So hello everyone, welcome to week 4 of CVEN4402 Transport Systems Analysis Networks. In this week lecture, we're going to cover methodologies on how to solve a traffic assignment problem. We'll talk about incremental loading as a method to solve traffic assignment problem. We will talk about some algebraic methods and also heuristics for larger networks. We will also cover how we can actually formulate the user equilibrium problem as an optimization, and then we'll try to derive the optimality conditions for that user equilibrium problem. In the last part of today's lecture, we will cover two iterative methodologies to solve user equilibrium problem, namely method of successive averages, or MSA, and the other method we will cover today is Frank-Wolf algorithm. Hopefully we'll have time to cover that. Okay, so let's get started. So as I said, I'm going to talk about traffic assignment problem this week, and we're going to talk about how we can actually solve traffic assignment problem. But before getting into the traffic assignment problem, let's step back and have a look at the general process for travel demand forecasting. Many of you have already seen this in some of your previous transportation courses, which is generally known as a 4-step model framework, where it has trip generation as the first step. So that's a step 1. Trip distribution is a step 2. Mode choice is a step 3. And traffic assignment is a step 4. So what happens is, in this travel demand forecasting process, we will start with some population and employment forecast. Then based on those forecasts and projections, we estimate how many trips will get generated. Then from those generated trips, we'll try to figure out how they will distribute around the city. This gives us the OD matrix. This gives us an origin-destination matrix. In the mode split or mode share step, we'll try to look into, now that we know how many trips goes from A to B, what is the mode split, what percentage drives their own car, what percentage takes public transport, what percentage take a bicycle, etc., etc. And at the last part, which is the focus of this course, is the traffic assignment part, where we try to figure out for those people who drive or who take a ride with somebody, which route they will take. Traffic assignment is not necessarily just limited to car traffic. We can have, we're not going to cover, we won't cover it in this course, but keep in mind that we will have a transit assignment as well, where you try to assign, for example, if somebody wants to go from A to B, which bus route plus train route or light rail or a combination of them will take. So which public transport route you take to go from A to B, for example. So that's a transit assignment. But the focus of this course is more on the car traffic side of the problem. And that's where we focus on this trip assignment. Also, another example of trip assignment is that you can also apply same concept to walking trips. So for example, if you want to walk from A to B, let's say it's a 1 kilometer walk, and which route do you take? And that gives us an indication of which footpaths will be crowded, which footpaths will have higher travel time, etc. So what goes into the traffic assignment is an OD matrix. It's a very important part of the input to the traffic assignment. And what we get out of the traffic assignment is the link volumes, the OD volumes, travel times, travel costs, and yeah, that's it. The majority of the, we can get a lot of other performance metrics out of the traffic assignment, like total travel time in the system, delay, etc., etc. But the main ones are this link and OD flows, and also the travel times, both link and path travel times. So with that, let's move to next slide, which is mainly trying to capture what I was giving you as a summary for the four-step demand modeling process. So if you start from trip generation, we'll look into how many trips go from some zones, which are my production zones. So this is production zones. Again, I am expecting you guys are a little bit familiar with these terminologies if you've had, and these are attractions. I'm sure many of you have had this course before, have had a similar course before talking about trip generation, distribution, and stuff. But anyways, this gives us some indication of an OD matrix where we um, get to know how many people go from, for example, zone 1 to zone 1, how many people go from zone 1 to zone 2 to zone 3 to zone 4, and the other way around. And again, in the mode choice, we take that big OD matrix and divide it into by mode OD matrices. So we will have a specific OD matrix for car, we will have a specific OD matrix for bus, for example, or a specific OD matrix for rail or walking, etc. So in this part, in this course, we'll focus on this OD matrix by car, and that's where the traffic assignment problem starts. Now that we have an OD matrix, or as I said, origin, destination, demand matrix, that's the right terminology, but we make it short and we just say OD matrix or OD demand matrix, OD trip matrix, they're all interchangeably used. Now the question is, which route would you or somebody will take going from A to B? So some of the inputs, if you want to refresh our memories, is the network model. I need to know the network structure, the topography of the network, where the nodes are, where the links are. I need to know the link cost function. Each link will have a cost function, a travel time function, which tells me the relationship between the volume on the road, volume on the link, and the travel time or the travel cost of it, and also the OD matrix, which is an important input to it. And the output, as we said before, as we talked before, is link flows, journey times, OD flows, path flows, and what kind of methodologies we look at when we want to solve traffic assignment. There are different approaches when it comes to traffic assignment. The the classical way of looking at it, or the most practically common way of looking at traffic assignment, is we call them equilibrium seeking. So equilibrium seeking methodologies, where we try to reach an equilibrium point, whether it's a user equilibrium or system optimal, but it's an equilibrium point where we want to reach. And that's what it's called, equilibrium-based assignment. We also have non-equilibrium methodologies where you don't necessarily reach an equilibrium. For example, you do a stochastic route choice, or stochastic route choice is a very good example here, which doesn't necessarily reach to an equilibrium point, but it gives you some stochastic outcomes at the end. But anyways, the focus here, at least in this week, is the equilibrium seeking part, where we want to reach an equilibrium point, whether it's being a user equilibrium, as we talked before, or system optimal, as we're going to talk today as well. So let's have a look at an interesting problem here. Imagine the network that we're dealing with is totally uncongested, and one very simple and maybe naive way of assigning trips to different routes is called all or nothing assignment, or AON, we sometimes call it AON, or all or nothing assignments, where we say for any given OD pair, for example, if I want to go from A to C, or if I want to go from A to D, from B to C, or B to E, for any given OD pair, all travelers are assigned to the route with the shortest travel time. So it's an all or nothing assignment, meaning that you assign all the trips for any OD pair to the only shortest path. So you don't really distribute them. So you just assign everyone to the shortest path for that specific OD. So in this case, for example, let's first try and figure out what is the shortest path from. So this is our OD matrix before I do that. So this is our OD matrix here, which tells me there are 400 trips going from A to C. So let me also erase these things here so you can see A and C better. So 400 going from A to C, 200 going from A to D, 300 trips going from B to C, and 100 goes from B to D. So let's find what is the shortest path from A to C. You can apply Dijkstra algorithm, for example, if you want to find the shortest path, or any other shortest path finding algorithm. But again, probably this is an easy case. I mean, you can manually, by just looking at it, can figure out what's the shortest path from A to C. So let's have a look. So if you want to go from A to C, this is the shortest path. This is the shortest path going from A to C. And if you apply Dijkstra algorithm, as I said, or as I said, any other shortest path algorithm, you'll find that going from A to D, this is also the shortest path problem going from A to D. And these numbers on the links are, by the way, the link travel time functions. It's not a function, it's actually a number, a fixed number in this case, in this example. So it's a fixed travel time. You want to go from if you want to travel through this link, the cost is 5 whatever units. It could be minutes, or it could be dollar values, or anything. So anyways, we apply the shortest path algorithm to find the shortest path from all the ODs, all the given ODs. So A to C, we have it. A to D, we have it. You can apply the same thing for the B to C and B to D. So this would be the shortest path going from B to C, and this one would be the shortest path going from B to D. And now that we have the shortest paths, it's very easy. Where the all or nothing assignment, what will happen is in all or nothing assignment, so now we're going to do an all or nothing assignment, okay? All or nothing assignment. We assign all the trips to the shortest path. So let's have a look. How many people are going from A to C? I have 400 people going from A to C. So this link, so I have 800 people I have 400 people going from A to C. So I'll have 400 people on this link, 400 people on this link, 400 here, 400 here, and they reach their destination, right? Now let's have a look at A to D. I have 200 people going from A to D. So I have an additional 200 people on this link, 200 here, 200 here, 200, 200, and 200, and they reach the destination. And if you want to get the link volumes here, you can see that the first link in this tree, in this shortest path tree, I had 400 people from A to C, and I had 200 people from A to D. So if I think I need to sum them up to get that this 600 volume on this link comes from this summation of 400 plus 200. 400 of them are going from A to C, 200 of them are going from A to D. But the rest of the path for A to C and the rest of the path for A to D, because it doesn't have any shared, it's not sharing any part of the path with another OD shortest path. It just carries that 200, and the other one on top carries the 400 trips just by itself. So there's no summation of OD volumes on any of them. So that's an all or nothing assignment example where you assign for every OD, you assign all the trips to the shortest path. And let's also do the same thing for B to C and D. So when it comes to B to C, so I have 300 people going from B to C. So this was the shortest path. So 300 here, 300 here, 300, 300, and they reach the destination. And for B to D, I have about 100 going. So I have 100 taking this link, and 100 taking this link. So, and they reach the destination, and there's no shared segment of these two paths. So we don't have such example for the other OD. And now let's combine these two and let's have a look. So, and now let's try to have the aggregated assignment flows, right? So now we want to see, now if you combine all these OD pairs, all these networks into a single network as it was initially, what are the link volumes? And so we're basically overlaying these two link volumes on top of each other. So again, let's have a look. This 600 remains the same. I had 400 people going from A to C plus 200 going to, let me see what happens. Yep. So I had 400 plus 200. I had only 400 here, so 400 remains the same. This is okay. This is okay. Where does this 500 come from? If I go back to here, let me erase some of these things here so you can better see. So this 200 I had for people going from A to D, and I also have 300 people going from B to C. This is basically the same link as this one. If you look at the original network, look at the original network. So this is the link that we are talking about. This link belongs to, it falls into this shortest path and also this shortest path. So this link is shared between two different shortest passes, one from A to C and B to C, okay? Same thing with the next link as well. So that means if you want to get the total link volume on that specific link, you need to look at what volumes, you need to sum up the volumes that goes through this link coming from A to C plus B to C. Yep. So if I go back to the slide here, so this 500 is actually as a result of 300 plus 200. So this 300 plus 200. Sorry, this gets zoomed in. Yeah, so this is basically the 300 plus 200. Same thing. Actually, no, this one goes down. So, and this one is the 300 itself. Um, is that it, or this should be 500 too? I believe. Is that? I think this should be 500, right? Let me check. No, actually. So no, this link is not shared. So I think I initially thought this link is also shared. No, so this was the shortest path going here. Actually, no, it goes, yeah, that's right. So this is A to C. No. This is A to D, right? Yeah, this is A to D. This is A to D, and this is A to C. So this link is not actually shared between any of the OD paths from originating from A. That link is only used by vehicles or trips going from B to C. So whatever that flow path volume is, it will be the same on this link. So going back to this one, yes, this 300 is correct. 200 is correct. 300 is correct. And the rest looks all right. So the only point I wanted to tell you here, I wanted to make here is, how do we get this aggregated assignment flows? You need to, so what we did here, we started with path flows. And from path flows, we get the link flows. So we knew 400 people are going from A to C, and we knew another 200 people are going from A to D, for example, something like this. Yep. So that 600 here comes from, as I said, 400 plus 200. And if you look at this link volume here, so if I erase that, so where does this 300 come from? I had 200 going from A to D, right? So this 300 is basically the 200 people going from A to D plus 100 people going from B to D, right? So this link is actually shared between two different paths, for A to D path and also B to D path. So there is 100 coming from this path. So the total would be 200 plus 100, which gives me 300 as the volume on that link. So that's how we aggregate the assignment flows. So we figure out the path flows, and then from path flows, we try to get the link flows. But what is not accounted in this example what is not accounted in this example? What are the potential issues that may arise? We didn't really take into account how many other people from other OD paths will use the same link. So you want to go from A to C, yes, the shortest path is something, but we did not consider that the shortest path will actually change as a result of other people also using the same links, not a combination of the same people on my OD. For example, if I want to go from A to C, if I want to go from A to C, there might be other people like me taking that path. In all or nothing, that's obviously the case in all or nothing assignment. But there are also people going from B to C that may also take the same route, so at least some parts of the same route that I'm taking. So what I'm missing here is actually the impact of congestion. Another issue that it may rise here is this fixed, and that is because this cost is fixed. So again, if I go back to the shortest path, that wasn't the cost. So where is the cost? So these cost values, these numbers on the links that we used to calculate the shortest path are fixed. So that means it's insensitive. It does not change if the volume on that link changes, which is not true, right? Because in reality, if I have more volume on a road, if I have more cars on the road, I expect larger travel times. So more people are using a link, that cost should go up. But in this example, that cost is fixed. So these are some of the problems or some of the issues that we didn't really account for in this example. But before we continue, I want to do a little in-class experiment, okay? So let me call this, this is you want to go, this is you want to go from here to here. This is your origin, and this is your destination. And you have three options to go with. You can go from path A, or take path B, or take path C. And each of the paths have a link cost. So this one is 50 plus 2x1. x1 is actually the volume of link A, or XA. This is 3x2. x2 is the volume on x2, the volume on this link B, or path B. And this one, xc, is actually xc, the volume on this path itself. So you can either take A, or take B, or take C, and you know the travel cost. You know the travel cost, as I said here. And that cost is a function of the volume. What you don't know is what is the volume, okay? And your objective is you want to get from your origin to destination as quick as possible, okay? So you want to take the shortest route. Which one is shortest? Which one is the fastest? So, but what are some of the complications when it comes to route choice? So congestion effects is a very common complication, because congestion affects the shortest path, resulting one path becoming more competitive than the other one. And how we handle this congestion? By just this use, very similar to this experiment that we just did, we handle it with user equilibrium. So we believe people over time will learn, and they will find the equilibrium point that is best for them, and there would be no other paths that they can switch to improve their travel time. There is also this complication that is related to perceptions, and that's what I was also touched a little bit on. People have different perceptions. Imagine I'm going from A to B, and you're also going from A to B. But I may have in my mind, I may perceive a route to be the shortest route, but you may have another route. You may believe, no, that's not the shortest route. Another route is the shortest route. I may say, hey, if you want to go to CBD, take the Anzac Parade. You may say, no, I don't want to take Anzac Parade. I think if I take M1, if I take the tunnel, that's the shortest path. So people have different perceptions because we don't really have the exact and complete knowledge of the network, right? People have different perceptions that which route is has the shortest cost for them. And when I say cost here, I mean, general cost. It doesn't necessarily have to be limited to travel time. It could be that you are more comfortable driving on a freeway than an arterial. So you think shortest cost path for you is the freeway, not necessarily because of the cost of driving in terms of travel time, but because of the cost of the inconvenience of having to stop behind so many traffic signals. You prefer to go to the freeway, and that has a value, that has a incentive for you, that has a negative cost for you. So basically, the cost of taking Anzac Parade is high because in your mind you have some mental or artificial costs related to stopping behind every signal. Or the other way around, you feel more comfortable driving on an arterial with trees and shade and passing through the Centennial Park. That gives you a better travel cost, you may think. So because of all these different perceptions that we have, route choice becomes a little bit complicated. And the way we handle it, we call that user classes. So we define different user classes. We can say the population has 5 different classes. Those people who value travel time more, those people who value, I don't know, shade and trees, those people who have a very high value of time, low value of time, different income levels, etc., etc. There is another complication in route choice, and that relates to knowledge. Again, in one of the assumptions in the user equilibrium is that we have a full knowledge of the network, meaning that I know other routes. I have a knowledge of alternative routes, and that is not true because sometimes I don't know how many, even if you want to calculate now, how would you go from UNSW to CBD, Sydney CBD? There might be tens of different routes, right? It's not only Anzac Parade and M1. You may take many different possibilities. But I don't have that knowledge. In my mind, I only have Anzac versus M1. Somebody else may have Anzac M1, another route. Someone else must have 4 possibilities in their mind. So because of these differences of knowledge that people have, that creates some stochasticity in the route choice. The user equilibrium doesn't account for that. User equilibrium assumes the population is homogeneous in terms of their understanding and knowledge of the network. They all have the same knowledge of the network. But in reality, that's not true. So the way we handle it is we handle it with a stochastic route choice, which I think towards the end of the course, I think week 7 or week 8, we'll cover our stochastic route choice. But anyways, so in the user equilibrium, we only take into account congestion. We can take into account different perceptions by introducing different user classes, but the problem with knowledge, the perfect knowledge, cannot be handled with user equilibrium, and one solution is going with a stochastic route choice. There are different methods, different possible solution approaches when it comes to traffic assignment problem. One method is called incremental loading, which we will go in a minute. We'll go over that in a minute. The other one is algebraic solution, where we set some simultaneous equations and we try to solve them. And then the last one is heuristics, which we will cover towards the end of today's lecture. So let's start with incremental loading. So imagine this is a network we have. It's a very simple network. I have 6 travelers going from 1 to 4. So this is my origin. This is my destination. So this is my origin. This is my destination. And I have 6 people want to go from 1 to 4. And there are 2 possible paths, right? This is one path, path A or path 1. And this is another possible path, and that is path B. And each link in the network also has a link cost, which is not fixed, right? You see, it is dependent on X value. X is the link volume. So I have 2 links here, 2 links here, and each of them has a travel time function or travel cost function. So link costs are shown. X is the flow on a given link. All links are 10 kilometers in length. And what we want to do now in this example is we want to compute link flows and average linkage speeds under UE conditions. I mean, for now, forget about average linkage speeds. Let's focus on calculate the link volumes under user equilibrium conditions. So one way of doing that is start by incrementally loading the network. And that is the incremental loading method that we're covering. So the way we do it is we say, okay, for now, let's start with nobody is in the network. 0 people is in the network, right? So what will happen? This is 0, this is 0, this is 0, and this is 0. So this is 10 multiplied 0. So overall, this is 0, this is 0, and this cost would be 50, this cost would be 50. So that both path A and path B actually have the same travel time now, right? So path A has a travel time of 50 or travel cost of 50. Path B cost is also 50. So if I want to incrementally load the network, the first person that wants to enter the network can actually randomly choose path A or path B because they actually have the same travel cost, right? They're both 50, and if you are the first person entering the network, you choose either A or B. Doesn't really matter because they have the same travel cost. So imagine the person chooses route A. Okay, so now what will happen? So that is incremental loading. We loaded one person into the network. So one person chooses path A. So what would be the new volumes? So this volume would be 1, this volume would be 1, this volume is 0, this volume is 0. So what would be the new cost on the paths? So this cost would be 51, this is 10, this is 0, and this is 50. So in total, path A, so this path A cost would be 61, and the cost associated to path B would be 50. Now let's load the second person. So first person has taken path A, okay? Now if you want to load the second person into the network, which one is the shortest route? Obviously path B is the shortest route now because it has 50 minutes or whatever the cost unit is here. 50 is smaller than 61. So the second person will obviously choose path B, right? And now we can actually recalculate the travel costs. So let's recalculate these things. So let me erase this. So it was 50 and 61 before. So now let's see what are the link volumes. So link volume, this is 1. This was the first person. And now the second person choose this path. So this is 1, this is 1. And now let's recalculate the path cost. So the first one would be still 61. And path B would be 10 plus 51, again, it's 61, right? So they become again equal. So now again, if I incrementally increase the loading, now imagine I load another person, the third person, person number 3 wants to enter the network. Which one he or she chooses, A or B, doesn't really matter. They have the same travel time. So the traveler will probably randomly choose A and B. So imagine he or she chooses A or B. I mean, okay, let's assume the person chooses B. So what would be the new volumes? So still on path 1, I have this was person 1, this was person 2. Now another person chooses path B, right? Traveler number 3 passes path P. So this would be 2 volume. This volume of the link, this link volume would be 2. This link volume would also be 2, right? Because 2 people are taking this path and only 1 person is taking this path. Now what would be the new path cost? So the new path cost on the top, path A still would be 61, and on the bottom would be 20 plus 52, and that is 72, right? So now, if we keep incrementally loading, you can see that the path cost keeps changing and switching. And if you keep doing this, again, I've done it here. And finally, traveler 6 will choose path B, and there you go. So if you keep incrementally loading, what you will end up is that you will end up with a case where either you get the exact equilibrium point where the path A and path B have the equal travel time, just like in this case, and you have 3 people taking this path and 3 people taking this path. And if you can see, the travel time of path A and path B are equal, so the user equilibrium conditions are met. And there you go, you solved user equilibrium. So that is called incrementally loading. But there is, I mean, I can ask an interesting question here. What if we only had 5 travelers? So we would have probably stopped here. So if we only had to load 5 people in the network, we didn't really have this step at the end, right? So what we will end up in this case is 83 plus 72, right? So it is not equilibrium, but you can argue it is close to the equilibrium because the travel times are close enough. So 83, 72, very close enough. Another argument is that you don't necessarily have to go with integer values of travelers. So you can actually assign half a traveler or instead of one traveler as an integer number. So what you can do at the end is you can say my increment is not one traveler by one traveler. Instead, I have half a traveler by half a traveler. So if you do that, what you will end up is, if your interval is half a traveler, you will end up by 2.5 traveler on the top path and 2.5 traveler on the bottom path, and you will end up with the same path travel time on A and B. So you would solve this problem of not having equal path travel times, but at the same time, I don't want to say you create an issue. It's not really an issue have a non-integer volume, but physically it doesn't make sense. We don't really have half a person, right, traveling. But in a very large network, I mean, that's okay. We do that a lot when it comes to traffic assignment. We sometimes go with non-integer numbers. So that's about incremental loading. We talked about brass paradox, I guess, in the first or second lecture, where we said brass paradox says if you have this network and people are selfishly just choosing their route without knowing or caring about how others are choosing the route, adding an additional link to the network may not necessarily improve the performance of the network. So in this case, if we add this link into the network, this new path will become the shortest path. And because people selfishly choose their path, everybody will switch to this path. And it actually ends up making it worse for everyone. And you can do that. You can actually, what I would suggest you to do, I'm not going to go over this example. We talked about brass paradox before, but this would be an interesting example for you after the class to try to, so this is the same network as we had in the previous example, right? So now the question is, add this new link with this cost function and redo the user equilibrium. So redo the user equilibrium with incremental loading. Okay, and see and try to solve user equilibrium with incremental loading and see what volumes you get. And when you get the volumes, calculate the link flows and calculate the path flows. If you do that on your own time, what you end up seeing is a very interesting result from the just very similar to what we covered previously in a previous slide, in a previous lecture, that you will end up actually in a worst equilibrium case. So the equilibrium solution for this new network with that additional link is that everybody will have 92 minutes as their path travel time. While if we did not have that additional link in the network, if I go back to the previous example we had, the path travel time, the final path travel time was 83. So we had 83 minutes per person in the previous example, and now with adding this additional link, we'll end up worse with 92 minutes. So what I would suggest you to do, please go over this example on your own time, apply user equilibrium to this network, and do the incremental loading, and get to these numbers, get to this 92 minutes. And then you'll have a better idea of how this brass paradox is actually affecting the user equilibrium solution. The next approach in solving a user equilibrium problem is called algebraic approach, where we try to set a number of simultaneous equations satisfying the equilibrium principles, and then we try to solve those simultaneous equations. So let's have a look at this example where we have two available links or paths, path 1 and path 2, connecting origin 1 and destination 2. The travel time for each link is given. So T1 is 2 plus x1 and T2 is 1 plus 2 times x2. So this is path 1 travel time, and this is path 2 travel time. Okay. If the demand is 5 trips going from A to going from 1 to 2, so 5 travelers is my demand. So 5 travelers going from 1 to 2. Determine the final link flow xi and the travel time ti on each link at equilibrium. So one interesting way of solving this problem is we can actually look at it from an algebraic perspective, where we can set up some simultaneous equations. So let me try to write it here instead of going through the slides, and we can. I hope you get a better sense of that in the next one. So what does user equilibrium say? User equilibrium says at the equilibrium point, all the used paths between any OD pair must have equal travel times. Or in other words, there are no other paths in the network for that specific OD that people can switch and improve their travel time. So that doesn't happen. So that basically means T1 must be equal to T2, right? So at the equilibrium point, in this example, if path 1 and path 2 are being used, the travel time of these two paths must be equal. So that's one equation. So if I replace the cost functions here, sorry, this should be 2. So that's one equation. We also have some demand conservation or flow conservation equations that we can write. And that is because I have 5 travelers going from 1 to 2, that means regardless of how many take path 1 and 2, if this is x1 and this is x2, x1 plus x2 must be equal to 5, right? Because nobody will disappear in the network. That is our demand conservation or flow conservation equation, where x1 plus x2 must be equal to 5, the demand. And having those two equations is enough to actually solve for equilibrium, because we have 2 unknowns, x1 and x2 are my unknowns, and I need 2 equations, 2 unknowns to actually solve it, right? So it's that's very easy. So we set the demand conservation equation. So demand conservation, and this is the UE principle. which says any used paths between an OD must have equal travel time. And if you put them, and if you solve this, if you solve these simultaneous equations, you'll get to see what is x1 and what is x2. And now that you have x1 and x2, you can actually put it into the travel time functions. You can put it into the, you can put it into the travel time functions and get the t1 and t2, right? So t1 and you can get t1 and t2 after you get x1 and x2. So from x1 you get t1, and from x2 you get t2, and you solved user equilibrium. So very easy. How about, I mean, I leave that to you to calculate the actual numbers. I'm sure you get the point what I'm talking about here. So you set two equations, two unknowns, and there you go. So how about we now add another link, like link 3. So T1, T2, and now we have T3 as well. So people have three options. You want to go from 1 to 2, same number of demands. So this will add another unknown to the problem, right? Previously we had x1 and x2, and now we have to find x1, x2, and x3 as my link volumes. So let's write down the equations. Again, T1 must be equal to T2. That's one equation. T2 must be equal to T3 as well. If all these paths are being used, all the travel times must be equal. Then my demand conservation equation would be x1 plus x2 plus x3 must be equal to 5. Now I have three equations and three unknowns, and then if I can simultaneously solve these three equations and get the answers, right? So again, that would be my demand conservation, and T1 equal T2 and T1 equal T3. So I have one equation here, one equation here. And if you solve this, you get x1, x2, x3. And as a result, if you put these x1 and x2 and x3 into the travel time functions, you get T1, T2, and T3. And very easy, you can calculate the user equilibrium flows. So if you want to summarize these examples into a generalized framework of system of equations that can be used to solve UE, is that we set an equation for user equilibrium conditions that if a path is used, its travel time must be equal to all other path travel times for that OD. We put one or more, depending on the number of ODs, depending on the size of the network, we put some equations together representing the demand conservations. So we must move all demand through the network. So all the demand should be served. You cannot keep, for example, out of 5, you only load 4 and you keep 1. So all the demand has to go through the network. All the demand must depart the source node, and all the demand must arrive at the destination eventually, right? We can also have some flow conservations, meaning that no travelers will be lost in the network. So imagine I have this node in the middle of the network that I have 2 links going into it and 2 links coming out of it, right? So imagine this is x1, this is x2, this is x3 and x4. If I want to write the flow conservation for this specific node, that means all the ingoing volumes should also eventually come out of the node, right? So x1 plus x2 must be equal to x3 plus x4. That's an example of flow conservation. And again, depending on how large the network is, you may have a couple of these examples that you could write the flow conservation equations for it. So here's another example where we have a more complicated network, and I have A as my origin and D as destination. I have a set of links, 1, 2, 3, 4, 5. The demand is 6. And the link cost functions for each of the links. T1, T2, T3, T4, T5. So if we want to write now now let's algebraically solve this problem that we want to find. The problem is asking, find the user equilibrium link flows and link travel times. So what we can do is we can first start by finding the paths. What paths exist between A to D? So there is one path here. There is another path here, right? Also this path. So I have three paths, right? So let's call them path 1, path 2, and this one is path 3. So I have three paths going from A to D. So again, the user equilibrium principle says if all these paths are used by travelers at the equilibrium, they must have equal travel times. But what is the travel time of path 1? Because now path 1 consists of two links. So path 1 consists of link 1 and 3. Path 2 consists of link 1, 5, 4. And path 3 consists of link 2 and 4. So the travel time of path 1, let me put P as a superscript, so that's path 1, is actually equal to Tx1 plus Tx3, right? So link 1 plus link 3, if I travel time of these two links, it gives me the travel on path 1. So same thing with path 2. What is the travel time of path 2? It would be travel time of 1 plus 5 plus 4. So it would be travel time of link 1. This x that I put here as a superscript represents the link, p represents the path, okay? 5 plus tx4. And the path, the third path, the travel time would be travel time of link 2 plus link 4. So it would be t2 plus t4. So these are my path travel times. And at the equilibrium, they must have equal travel time. So that means I can actually write two equations alone from this UE condition. And that would be travel time of path 1 being equal to travel time of path 2, and travel time of path 2 being equal to travel time of path 3. So these two equations, I've set them aside. There are a number of other equations that we can write here, right? So let's have a look. How can we write the demand conservation equation? So demand conservation equations looks at the origin and destination. So it says all the demand, the sum of the demand, all of the demand will come out of the origin, and all the demand will be eventually finished or reach destination. So that means, so let me erase these paths, okay? So what does that mean? It means if this is x1 and x2, all of the demand should come out of the origin. That means x1 plus x2 is equal to 6. And also if I look at the destination, all the demand will eventually reach destination. So x3 plus x4 must be equal to 6 as well. So I have two additional equations here as well. I already had two equations from the UE principle. I can also write two other equations for flow conservation, right? So what does flow conservation says? At any node in the network, travelers will disappear or appear. That means if I look at node B, this is x1 going into B, and I have x3 and x5 coming out of node B, right? So that means I can actually write x1 must be equal to x3 plus x5 because nobody has to appear. I can do this. I can do the same equation. I can write a similar equation for node C, where x4 is the number of travelers coming out of node C, and I have x5 and I have x2. So x4 must be also equal to x2 plus x5. So how many unknowns do I have in this problem? I have 4 link volumes that are unknown. So I have 5 unknowns, and I already have 6 equations, right? 1, 2, 3, 4, 5, 6. And 6 equations, 5 unknowns. If you simultaneously solve these equations, you should be able to get the answer where you can find x1 to x5. And then when you have all these link volumes, you can actually put them into the equations of the travel times and get all the travel times. Okay? And again, I leave the calculation of the numbers to you. What I'm trying to focus now is more to show you how this algebraic framework works, and the rest of solving the simultaneous equation is very easy, and you can do it on your own. Yep, we talked about this. This is all what we talked before: demand setting, equilibrium conditions, setting the demand conservation, flow conservation. And if you solve them, you actually get to the link volume like this. And if you put it into the you can also get the path cost if you put it into the path cost formula that we found. So if this is path A, it would be the travel time of link 1 plus travel time of link 3 gives you the path travel time. And because at the equilibrium, all paths have the same travel time, you can actually verify. You can also calculate the path travel time for this path and see whether it gives you also 92 minutes. And you can do the calculations and verify your answers with the numbers that I have on this slide. But I leave that to you to do the rest of the calculations. I mean, nothing very different, nothing very difficult from here. There's another thing called TSTT. What is TSTT? TSTT stands for total system travel time. So total system travel time. And that is the summation of the link travel times. So for example, if I have, so these are all the summation of the link travel times. So the travel time of link 1, travel time of link 2, travel time of link 3, travel time of link 4, travel time of link 5. If you put the associated link volumes into these travel time functions, and if you sum them up, you get something called total system travel time. And that is one performance measure that we'll get to see later in today's lecture. I mean, when we want to solve system optimal problem, we will actually try to minimize this total system travel time, or TSTT. So moving on to link performance function, in many of the examples so far that we looked at, if I go back to the previous slide, so look at the link travel time functions. The link travel time functions are very simple, like 10 multiplied by x1 or 50 plus x2. In reality, the link travel time function actually looks very different than this. So the travel time function looks more like an exponential function, where this is my x, if this is my t, this would be how it looks like. And a very common function that we use for real traffic assignment problem is this function that is called BPR function. BPR stands for brew of public road. Brew of public road, I guess from the UK, many years ago, 1960 or 1970. And it actually gives you the travel time as a function of the volume of the link. And the function, what it has inside is the free flow travel time. When nobody's in the network, what would be the travel time? It has the volume of the link, it has the capacity of the link, and this alpha and beta are the parameters of the model that we can calibrate and find. And if you have real data, imagine these dots are real data, and you fit this curve to the real data, and you find the alpha and beta, and you use it into this equation. But what properties should link performance functions have in your idea? If you want the equilibrium problem to have a unique solution, the link performance function must be monotonically increasing. So in this case, this BPR function is monotonically increasing. It looks like this. But if the travel time function was not monotonically increasing, meaning that it was like this, for example, okay? If it was like this, we can actually prove that the equilibrium problem will not have a unique solution, meaning that you may have multiple solutions for the same problem. Just like, again, if you put simultaneous equations, if you want to solve simultaneous equations, not necessarily all simultaneous equations give you a unique answer. You may have multiple answers that satisfy your simultaneous equations, right? So having a monotonically increasing travel time function ensures that the user equilibrium problem has a unique solution. So this is another example, the same example as we had before, where we have two links in the network. I have 7,000 vehicle going from 1 to 2. And now we're using the more realistic travel time functions. That is the BPR function. And in this case, alpha is used as 0.15 and beta is used as 4. So you see this 0.15 and 4. That's the alpha and beta we use in the model. And this 4,400 in the denominator, that's the capacity of link 1. And this 2,200 is also the capacity. Okay? And again, if you want to solve this problem, you can solve it by incrementally loading the network or algebraically. If you want to algebraically solve it, it's very easy. Again, as I said before, you only need two equations because you have two unknowns here. You set T1 equal to T2, and you set X1 plus X2 is equal to 7,000. And then you solve the simultaneous equations and you find X1 and X2. Okay, but probably because the function looks a little bit more complicated, solving it wouldn't be as easy as some of the more linear functions that we used in the previous examples. But again, I leave this solution to you. Again, nothing too complicated here. You know how to put the simultaneous equations. It's just a matter of solving it numerically and get the answer x1 and x2. But what is interesting is if you actually plot these two travel time functions against each other in a graph like this, where you have x on the bottom and you have the travel time function on the y-axis. So that means what will happen here is, so this is the travel time function of path 1. This is actually path 2, sorry, and the blue ones is path 1. So the travel time function tt of path 1, okay? And again, user equilibrium, we said T1 should be equal to T2, right? So the travel time functions must be equal. What does it mean graphically? Graphically, it means these two equations must intersect each other, right? And that is another way of trying to think about equilibrium, that if I find the point that those two path travel times intersect, that intersection point gives me the user equilibrium volumes. So in this case, this 3,000 something would be my x1, and x2 would be simply 7,000 minus x1. And you can graphically try to get a sense of where that equilibrium point is and what would be x1 and x2 in this example. So that's the equilibrium points. And now what we can do is we can actually see how does capacity affect the user equilibrium solution. So in the same example as before, if we increase the capacity of this path from 2,200 to 4,400, what will happen is if we again plot the curves, where on the x-axis we have x1 and the y-axis we have the travel time. And if you plot these two curves, you can see that these two curves do not intersect. What does that mean for the equilibrium? Does that mean we do not have an equilibrium point, or does that mean one route is being used and the other route will not be used? The answer is we will still have an equilibrium point, but because the travel time of route 1 is consistently larger than the travel time of route 2, this route will never be used by people because this has a very large time. And the equilibrium points is actually here, where all the 7,000 people, right, will choose, actually not here. This is x1. This is x1. So this is t2. So it should be 0. So this is actually the equilibrium point, where x1 is actually 0. So this equilibrium point is x1 is actually 0. That means x2 is 7,000. And if you put it into the equation, you can actually get the reason path 2 is being selected is because this number is smaller. I mean, the rest is the same. So path 2 will only be used. Path 1, which was this one, will never be used by anybody. And all the 7, so this one would be 0, and this one would be 7,000. And that is still equilibrium, because what the user equilibrium was saying that the used paths will have equal travel times. So if a path is not used, you don't have to worry about it. If a path is not used, its travel time must not necessarily be equal. I mean, it doesn't have to be equal to the travel times of the used paths. Or maybe in a better, if I want to put it in better terms, is that if a path is not used, that actually means that path must have a higher travel time than the used path. Because if it has an equal or lower travel time, people would have switched to that route, right? But in this case, because path 1 has a very high travel time, everybody is using path 2. So at the equilibrium point, people are still happy with path 2. Nobody is going to switch to path 1 because path 1 has a higher travel time. And in this case, there's no other option. So yes, we're at the equilibrium point. There was a question, I believe, in the chat box. Let me come to the chat box. So why the travel time will decrease when volume increases? It's not decreasing. It's because the x-axis is x1. It's not x2. So each function, so t1 is a function of x1, t2 is a function of x2, and this x-axis is actually x1. So if you want to look at it this way, this is how we can picture it. And this is T1. So T1 is increasing with X1, right? T1 is increasing. Let me actually choose a different color. Maybe I choose green. Yes. So T1 is increasing as X1 is increasing, right? But the other one, you shouldn't look at it this way because the x-axis is X1, is not necessarily X2. So another way of looking at it is that X1 is 7,000 minus x2, right? So if you want to look at T2, you shouldn't look at it from left to right. If you want to see that monotonically increasing trend, you should look at it this way, that as x1 goes down, that means x2 is increasing, right? As x1 goes down, that actually means x2 is increasing because it's only 7,000 minus the other one. So this travel time is actually increasing. As x1 goes down, travel time goes up for the other route, right? As x1 decreases, as x1 decreases, it actually means x2 is increasing. So the travel time 2 is also increasing. So travel time 2 is increasing, travel time 1 is increasing, and that's how we actually look at it. Again, the point is the x-axis here in this plot is x1. If you want to plot them separately for x1 and x2, so if this was x1 and this one x2, this would be x1, this would be x2. So with that, let's move on to the generalized iterative approaches. So this iterative approach is the third method, okay? So far we've talked about the incremental loading. We talked about algebraic approach, and the rest, and this one is about iterative approaches or heuristics. So for any given OD pair, we select a set of passes that we think people will use, or we call them feasible passes. We write the equations for the travel times of each path as a function of the path demand. We solve the system of equations, and then we verify if this path is correct or not, just like the examples we had, right? But the problem is with the system of equations, or the problem with the incremental loading, is that how will you apply that to? I mean, it's okay for a 3-path network or even 4 or 5-path network, but as the size of the networks gets very large, like in real cases, like this is Chicago's network. This is Chicago. I mean, if you look at Sydney network, Melbourne network, Beijing network, it's very huge. So it's not really practically possible to solve them by incrementally loading or by solving some tens of thousands of simultaneous equations, right? It's not really possible. So that's where we need some scalable methods, some methods that can be scaled up to bigger problems. And that's where this iterative framework comes into play, that you first start with calculating path travel times. You find the shortest path. So here, this arrow is, for example, Dijkstra algorithm. You apply shortest path algorithm for any OD. For all the ODs, you find the possible set of paths, the shortest paths, and then you adjust the path choices towards equilibrium. So you shift some people from one path to another path somehow, which we're going to see how, and then you recalculate the path travel times. You recalculate the shortest path, and then you keep doing this iterative framework, many iterations until you reach the equilibrium point, okay? So that's what I mean by iterative framework. Before going through that, we need to define mathematically some terminologies, because we need to put some mathematics and formulas here. So link flows, link travel times, path flows, path travel times, and link path relationships. These are the main notations. We need to first define and put some mathematics notations to these terminologies here. But before that, I mean, we talked about this, that link performance functions, they look like this usually. They're monotonically increasing, and they usually have an exponential term. And like this is the BPR function we use. We talked about this. So if I want to put some notations here, let me do that here. I mean, I think I have it in this slide. Okay, I have it in this slide, so I don't have to put it here. But anyways, Xij is my link flow, right? Tij is my link travel time. Tij0 is called free flow travel time, meaning that when nobody's on the network, what is the link travel time? Cij is the capacity of link ij, and as we talked before, alpha and beta are parameters, model parameters. So let's go over some of the notations as we talked about. So these are some of the mathematics notation this is widely used in the literature around the world. Okay, so if you get a paper on traffic assignment, they will probably use the same notations, most probably use the same notation. So this is how we define a network. We say A network is defined as G with n set of nodes and A being the set of arcs. So n is the set of nodes and A is the set of arcs. We can also define some centroids. You know, remember the first slide where we said this is the city, we have to break it into different zones, and then each zone may have a centroid. So, you know, we can also define some zones, you know, and centroids. But again, we don't have to do it now because we only focus on the assignment part, not necessarily the trip distribution and generation part. But anyways, you can also define some centroids being a set of this n itself. So an origin destination matrix, this is how we represent it. So DRS, where so this is a matrix, right? So this is a matrix. And DRS alone outside the matrix format is basically the number of people going from R to S. So DRS is the number of trips going from R to S, R being part of this centroids or origins, and S being the destinations from origin. So R is the origin, and S is the destination. Okay, so DRS is the demand, and if you put it in a matrix format, that's your OD matrix. So what is IJ? IJ basically is a link. IJ is a set of arc set if it connects node I to node J, and I is also called tail or upstream, and J is head or downstream. So if this is I, this is J, this is IJ. Again, remember IJ and JI are different because it has directionality. Transport networks have directionality. So this is IJ, and I is called upstream or tail, and J is called head or downstream. I'm more comfortable with upstream downstream node rather than tail and head, but you can also use tail and head terminology. As we did before, VXIJ represents the flow on the link IJ, and TIJ represents the travel time of the link XIJ. Okay, so these are some notations that we're going to use now. There are a few other more things we need to cover, and that is called how can we define a path? So imagine I have a network. Oops, sorry. Imagine I have a network, and this is a path consisting of two links. So this is one path, and it has link 1 and link 2, right? So this path, we can actually use the symbol pi for it. So path pi is a sequence of n adjacent links, in this case 1 and 2, for example, connecting all the nodes along the way. So if I want to write it more precisely, it would be pi is actually a set of paths. So this is link 0 to 1, this is link 1 to 2, this is link 2 to 3, and all the way to k minus 1 and k, right? So imagine this is a pass. So if this was 0, 1, 2, 3, so this 0, 1, 1 to 2, 2 to 3 are the links, and then this pi is a sequence of n adjacent links. And if you want to write it more compactly, you can just say, you know, I0, I1, I2. When a path is a cycle, when is a path a cycle? A path is a cycle if the start and end point is the same, right? A path is a cycle if basically I0. So remember, so look, IK was the last node and I0 is the first node. So a path is a cycle if I0 is equal to IK, right? A path is cyclic if it contains a cycle, and acyclic if it doesn't, obviously. A network is acyclic if there are no cyclic path in the network, obviously. So anyways, let's have a look at this example. Again, this is the same thing as I covered before. So this is a cyclic network because we have a cycle here. So there's a cycle here. So the network is not cyclic. And there are also some, there's actually another cycle here as well. Let me choose a different color, maybe red. So there is one cycle here, 3, 2, 3. So that's one cycle. There's also another cyclic path, 1, 3, 2, 3, 4. So going from 1 to 1, going from 1 to 3, and then to 2. Oh yeah, that's a nice cyclic path. So look at this. You go to 3, you go to 2, and then you come back to 3, and then you continue. Would you ever take such a path? The answer is no, because it doesn't make sense to go through this cyclic path. Why should you go down and then come back up again and then go if there is if the straight path is available? So if this path is available, nobody will take this path, right? It doesn't really make sense for people to take that path. So the network is cyclic. So network is cyclic. And it also has cyclic paths, but used paths, the paths that people use, will not be cyclic. Okay. So let's continue with some notations. So we said we use the notation pi for the set of paths, right? So actually, this is now a capital. Is this a capital pi? Yes. So we use this notation to represent the set of acyclic passes. So we know, so if you want to define a set of feasible passes, you never include cyclic passes when you want to do the assignment because people will not take cyclic passes, right? So this capital P here, big pi here is the set of feasible acyclic passes connecting R and S. A small f is the path flow. So FRSK is basically, so K is the number of path, because imagine this is path 1, this is path 2, this is path 3, right? And this is R, this is S. So if I want to write what is the path on path 1, path 2, path 3, this is how we distinguish it. So we say F R2S1, F R2S2, and FRS3. Okay, so this FRSK is the path flow. Remember, volume flow was Xij, right? So Xij is the volume flow, FRS is the path flow. And F is a feasible assignment if the following conditions are satisfied. What conditions? Let me see if I have it here. Yes. So we would say F is a feasible assignment if these conditions must satisfy. What are the conditions? Obviously, the path flows must be non-negative. So none of the paths in the network can have negative flows, right? So that is a non-negativity condition. For all the K, all the passes that belong to RSS are a set of the acyclic passes. For all the RS, all the origin and destination, being the set of the centroids as we defined earlier. The other condition to meet is the no vehicle is left behind, meaning that the summation of the path flows must be equal to the demand. This is basically the same thing we did in the simultaneous equations. If this was my origin, and this was, imagine this is demand, right? Imagine this is the demand going from R to S, and this is my FRS1. Sorry, 1 should be on the bottom. FRS2. So FRS1 plus FRS2 must be equal to DRS, right? This is the demand conservation, right? Remember the simultaneous equation, demand conservation. So no vehicle is left behind. And this is how we can write it down here, that the summation of all the path flows, the summation of all path flows over what? Over all the passes for each origin destination. So for each origin destination RS, if you look at the feasible path, this capital pi here, this big pi here, which has only the acyclic passes. So for all the passes, in this case, k is equal to 2. Like in this example, as I said, k was equal to 2. So this is basically can be written as the summation of k FRSK should be equal to DRS, right? DRS should be on the bottom here. DRS, right? So the summation of the path flows over all the possible passes between an origin RS must be equal to the demand. So that's the demand conservation. So these two conditions must be satisfied, okay, for feasible assignments. There is also another thing called link path adjacency matrix. This is very important, guys. So look, in this example, I want to go from 1 to 5, okay? How many passes exist? How many links do I have in this network? I have link 1 to 2, I have link 2 to 4, I have link 1 to 3, I have link 3 to 4, I have link 4 to 5. So I have 5 links, right? So let's say x1, 2, I can actually say I. So it's, I mean, let's put volume here for now. So x1 to, this is x2 to 4, x1 to 3, x3 to 4, and x4 to 5, right? I have 5 links and these are the volumes of it, but I have only 2 paths, right? So if I go with red, I have this path, path 1, and I have this path. This is a small pi, path 2, right? So now, how can we form a matrix that can tell me which link belong to what paths? Because a link, I mean, we saw this in previous examples that, for example, this link 4 to 5 actually belongs to both path 1 and path 2, right? So the whole idea behind putting together this new matrix called link path adjacency matrix is to tell us more information, to give us the information about the structure of the paths and the links, that which link belongs to what paths. So in this case, we have links on each row represents a link and each column represents a path. So in this case, if you want to write it down, let me erase these things. So we go with the notations that I have on the slide rather than the notations that I just made up. So I have path 1 and path 2. So this is path 1, this is path 2, and I have links. So if I want to write down the link numbers on it, that's probably easier to go with. So this is link 1, 1 to 3 is 2, this is link 3, link 4, and link 5. So look at this first column. So path 1, which links does it include? It includes link 1, 3, and 5. So 1, 1, 1. So for link 1, link 3, and link 5, I put 1. For link 2 and link 4, I put 0. How about path 2? So let's go down and let's go here. So 1, 2, 3, 4, 5, 1, 2. So path 2, it consists of link 2, 4, and 5. So this is 0, this is 1, this is 0, 1, 1, right? You got it? So this is how we put link path adjacency matrix. So this matrix tells us which links belong to what passes, okay? And there could be some links that are shared between two different paths, like link 5 is a shared link between path 1 and path 2, while link 2 and 4 is only used by path 2, and link 1 and 3 is only used by path 1. So anyways, all of that was notation to get to this point, because we want to formulate the user equilibrium problem as an optimization problem. That's why we're doing all of this. Let me see, what time is it? It's actually 2:18. So let's take a quick break, okay? 5 minutes break, and then we'll come back. And then we'll continue on how we can actually continue putting all these things into mathematical notations and formulas, so we can actually use that to write the UE optimization problem. This is what we are going to use a lot, okay? So this equation here, let's see what that is. It says XA is the link flow, right? So again, here we say A, instead of using IJ, let's now use, so instead of saying XIJ, we are now going to use XA as the link. It's easier to work with, right? And the way we're going to handle this is, it's a lot of summations. So summation over all the origins, all the destinations. So this is summation over all the origins. This is summation over all the destinations. And this is summation over all the paths, right? So this is summation over the paths connecting R and S, the feasible passes, the acyclic passes. And then how can we get the link flows from path flows? So the question that we want to answer here is, how can we get link flows from path flows? Okay. The answer is using the link path adjacency variable, and use this formula. So this delta here, is that delta or sigma? That's delta, right? Yeah. So this delta here, this small delta here, so this delta RS AK is basically representing that link adjacency matrix, link path adjacency matrix that we were talking about. Each of those variables inside that matrix is represented by this delta RSAK, which tells me, and it's a 0 and 1 value, right? This is either 1, or 0. So it is 1 if the link belongs to the path. It is 0 if the link does not belong to the path. So what will happen here is some 0 and 1 values. So this is 1 or 0, right? Some 0 or 1 values gets multiplied by the path flows. And if a link belongs to a path, or let me put it this way, if a link is shared by two paths, that link in the link path adjacency variable actually will appear 2 times on 2 different columns. So when you multiply this delta RSAK by the path flow, and if you sum it over all the origins and destinations and the possible passes, you can actually get the link flow of that. Again, to make it, let me make it a little bit more clear by going back to, let me make that example here. Let me make a very simple example. If I tell you, so this is FRS1, and this is FRS2, right? Imagine this is 100, and this is 200. Now the question is, what is x5? What is the value of x5? I mean, in this example, it's very simple, right? Because you can just visually see that, yes, 100 people plus 200 people. So this would be 300. But now imagine it was a little bit more complicated. It was a large network with a lot of shared links between many different paths. And that's where this matrix come into play, because we say, so in this case, I mean, let me write it down again. The summation of over all the origins, over all the all the destinations, over all the possible passes of delta RS AK multiplied by FRSK. In this easy example, we can easily remove the first two summations. Why? Because there's only one OD, right? So there is no summation over all the ODs. So there's only one OD. So let me get rid of the first two summations. We only have two paths, right? So this summation, this is K, would be either 1 or 2, right? We have path 1 and path 2. And let's see. So if you want to multiply this, is you can actually write it in a matrix format as well. So this would be this matrix, which is a by k. The dimension is a by k, right? Multiply by imagine I want to get the let me go back to this slide. I guess it's better to go with here. Oops, sorry. Oh, actually, I have an example here, so that's good. Let me go with this example that I have here. I was trying to write the same thing here. So if you want to put it in a matrix format, that's how it looks like, but don't worry about the notation here. It's not important. What matters is the example here. So if this is my matrix, if this is my sigma, all these arrays inside this matrix represents my RSAK, delta RSAK, right? And this is my FRSK. This is path, I mean, here in this case, I have 15 and 10. So this is FRS1 is 15, and this is FRS2 is 10. Okay? So if we multiply this adjacency matrix by the matrix or the vector basically representing the path flows, what I end up with is so this is A by K, the dimensions, right? And the dimensions of the other matrix is what? K 1, right? So K is the number of paths. So then therefore, if we multiply these two matrices, the resulting matrix will be A by 1, which is exactly correct. And A is the number of links, right? So this would be the x1, this would be x2, this would be x3, x4, and x5. So if we multiply the path link adjacency matrix by the vector of the path flows, we get as a result a vector that gives me the link volumes. And that's how we can get the link volumes from path flows. Okay? It's very simple. The whole magic is inside this adjacency matrix as we put it together. We can also put a similar relationship between path and link travel times. So if TA is the link travel time, and again, this delta RSAK is again the link path adjacency variable, how can I get the path travel time? So it's capital CRSK. Capital CRSK represents path travel time. So if you want to convert, so now the question that we want to answer is, how can we get path travel time from link travel time? We can use this formulation again, given that link path adjacency variable or matrix. So, and this summation is summation over all links, right? So summation over all links. So if you multiply that variable by the link travel times, that adjacency variables by the link travel time, you get the path travel time. And if you want to put it in in a matrix notation, it looks like this. You don't have to worry about the notations. But if you remember, this was transpose. Remember the transpose notation from matrix functions. So if I want to show you an example, the only difference between the relationship between path and link volumes and path and link travel times is that we use, when we want to calculate the path travel time from link travel times, we use the transpose of the adjacency matrix that we used before. So this is basically that. This is the transpose. So this matrix is the transpose of the original adjacency matrix we saw, right? It's shift the location of the rows and columns to get the transpose matrix. So anyways, this is the transpose matrix of the adjacency. And if we multiply it by the link travel time vector, so this is basically my TA vector. And again, this would be K by A. And this one has A rows and 1 column. So the resulting matrix is actually K by 1, right? So, and these are my C RSK values. So this tells me if this is link 1 and this is link 3 and this is link 5, what would be the travel time of path 1? The travel time of path 1 is simply 1 multiplied by 3 plus 1 multiplied by 8 plus 1 multiplied by 10, because zeros gets, it's just a matrix if it's just multiplying two matrices. So it would be 3 plus 8 plus 10. In other words, it's easy, right? So you want to just sum the link travel times to get the path travel times. But the reason we try to put it in a matrix format and in this notation is because, again, in a very large network, if you want to solve it, you can't really solve it by looking at it and, and if you want to program it in a computer code, you have to have these matrix formats to be able to calculate things very quickly and easily. So it would be 3 plus 8 plus 10, which is 21, right? So this will give me the path travel time. Let me see if there was a question in the chat box. I heard a beep. Yes, there are 2 questions apparently. There's one. Is the link travel time here fixed? It doesn't have to be fixed. No, not necessarily, but it could be a function. For example, this could be the travel time on this, for example, T1 could be, I don't know, 2x1 plus 10. But for any given value of x, for any x1 value, you end up with one value of T1, right? So for any given value of x, you get a single travel time value because of this function, right? And then that's where you use, so this is T1, T2, T3, T4, and T5. And as a result, you get the C1 and C2, the path cost. But no, T could be a BPR function, anything. But as I said, you have the x value in it to get the value of t, and then put it into this matrix format to get the path travel times. Let's move on. And so given all these path and link dependencies, this is how it works out. We find when it comes to the traffic assignment, this is how we do it. Iterative by iterative, this is how we work out. We start with some path flows. From the path flows, we get the link flows using the link performance. And this part is using that adjacency matrix if you want to get from path flow to link flow. And then using the link performance function from link flows x, you get the link travel times. And then how do you go from link travel time to path travel time? Again, using that adjacency matrix transpose you get the past travel times, and then you update again. You find the shortest path, you do the assignment, you again find the x's, you find t, you find c, and then we continue this in an iterative manner. Okay, so that's how the general dependencies of the path and links work together. So now all of that was background actually to formulate the traffic assignments as a optimization problem. But before that, let's refresh our memories with regard to the optimality conditions that we learned last week on one-dimensional optimization problem. So we said if we have one-dimensional optimization problem, meaning that you only have one decision variable, you could set up some optimality conditions. So if you find an x, if you find the value for x that satisfies all these three conditions, then that x value, you can be sure that's your optimal solution. And these optimality conditions was the non-negativity condition for x, and the derivative being positive or equal to 0, and if you multiply x by the derivative of it, it has to be 0, meaning that either x is 0 or this derivative is 0. So again, if you go back to the previous lecture, last week lecture, you see more information about this. But if we keep going, and now if you remember, we said, okay, how about we have more than one decision variable? How about we have two decision variable? And also, how about we have a linear equity constraint here? So from last week, if you remember, we introduced a technique called Lagrange multiplier, where we try to bring in this added constraint into the objective function and create a Lagrange function by itself. So we put the Lagrange function like this. We say this is the original objective function, right? So this is the Lagrangian function. And this is the dual variable, if you remember. So dual variable. And this is the constraint that is brought into this Lagrangian function. It used to be x1 plus x2, let me go back, equal to 5. Sorry, equal to 5. So if we can actually write it that as 5 minus x1 minus x2 equal to 0. So this part is actually brought into this constraint, a reformatted version of the constraint is brought into this Lagrangian function. And the way we said we can find the optimal solution for this is again using the optimality conditions when we set the gradient of the Lagrange function equal to 0. And that's we get the general optimality conditions. Remember this? So if you have an objective function with more than one decision variable and you have a linear constraint, you put together the Lagrangian function. And these are now the new optimality conditions, the more general optimality conditions that you have to satisfy to get the optimal solution of the problem, where you have to find the derivative of the Lagrange function with respect to every decision variable. You get the derivative of the Lagrange function with respect to each dual variable, the non-negativity constraint for the decision variables, and also this decision variable multiplied by the gradient of L being equal 0, meaning that this is either 0 or this one is 0. So if these optimality conditions are met, you can be sure that each of the xi's that you get are the optimal solution for the problem. We talked about this. And before we actually, we're going to use this now to formulate the UE, the user equilibrium as an optimization. But before that, let's first go over the system optimal because it's much easier to understand, and then we'll go to the UE. So what is SO? What is system optimal assignment? So in contrast to UE, which we said people selfishly choose routes, system optimal actually says we try to find the link volumes that minimizes the total system travel time. So that is actually let me try to bring my mobile phone for the time, so I don't lose track of time. Yeah, we are almost done, unfortunately. So for the system optimal, we try to minimize the total system travel time. Instead of, so people will choose route, will no longer choose route selfishly. Rather, they think about what route should I choose to help minimizing the total system travel time. So it minimizes the summation of the travel time of all the people in the network. So it's good for the society. It's the best outcome for the society, but it doesn't necessarily help individual people. It doesn't necessarily give you the shortest travel time that you could get. And the way we put this into an optimization problem is that we, as I said, we try to minimize the total system travel time, TSTT. Okay? And this is, and how can we put TSTT into equations? So TSTT is actually, if I have a network, and for each of these links, I have the volume and the travel time. If I multiply the volume by the travel time, multiply by the travel time, and if I sum this over all the links, sum this over all the links in the network, this gives me TSTT, right? So that's the total system travel time. Now, so the objective function in system optimal assignment is basically minimizing this TSTT. So if you want to minimize TSTT, so minimizing TSTT, which means minimizing the summation of XA multiply. I don't want to write the multiply again. So I just say XATA summation over all the links in the network. And this XA here is basic, it's not multiplying. This is like T as a function of XA. Okay, so this TXA here is FX. Okay, so this is travel time as a function of XA. So this is basically XA multiply TA. If you sum it up as a function of all over summation over all the links, it gives you the total system travel time. And you want to minimize that, but subject to some constraints. What are the constraints? The constraints are the path flows must be feasible assignment, meaning that it doesn't have it must not have it must not it must not it must not have it must not include cyclic paths, and also the link flows must be consistent with the path flows, meaning that you want to make sure that the relationship between path flows and link flows are met. So two equations. One is the non-negativity of the path flows, and also acyclic being acyclic, and also the demand conservation, which is again related to the first constraint. So this is demand conservation. Remember, the summation of the path flows must be equal to the demand. And the second constraint is actually the relationship with which we just went over to use that link path adjacency matrix. So this ensures that the link volumes we get, so this was link volume, right? Link volume. That the path volumes are correctly converted to link volumes. So this was path volume. So subject to these constraints. So now if I want to put it into an optimization format, this is how system optimal optimization looks like, which we want to minimize the TSTT, summation over all the links of XA multiplied by TA, and this ensures demand conservation. So this is demand. Actually, I have it written here, so I don't have to rewrite it. So the first constraint is summing flows over all the passes to give me the link flows. So ensuring the relationship between path flow and link flow are satisfied. This gives me the demand conservation, moving all the demand through the network. And this is the non-negativity of path flows. But now, so this was system optimal, okay? So this is system optimal, easy to understand. Now, how can we put together a similar formula, a similar optimization for user equilibrium? So now let's have a look. What would be the right objective function for user equilibrium? The answer is not really obvious. And it turns out it's the Beckman function. That's what we call the Beckman function. So user equilibrium is equivalent to this objective function, which says we want to minimize the summation of a term over all the links. So summation over all links. But what is this term? This term is basically the integration from 0 to xi of the travel time function. What does that integration mean? That integration is basically the area underneath the travel time function, right? So if this is x, this is t, and if this is my travel time function, and the volume of the x is this here, this integration gives me this area, right? So this is the integral from 0 to xi of ta, correct? And again, let's put like, I don't know, dw, so the integration looks more complete. But why this is equivalent to selfishly choosing a route, user equilibrium? I mean, I can talk about it next session, but let me finish. I mean, we can think about it and we can talk about it later, but let's first finish the formulation of the optimization before we run out of time. And then we can come back to that later, or I can email you more description about what is this Beckman function, how can you interpret this integration to be equivalent to the UE principle. But anyways, this is our objective function in UE. So this is our UE objective function, but subject to some constraints, right? So subject to the same constraint as we talked about before in the SO optimization, in the system optimal. So this is my UE objective function, which is the integral of 0 to xa of the travel time function, subject to the constraints related to the relationship between path flows and link flows, demand conservation, and the non-negativity of the path flows, right? So this is how UE can be formulated as an optimization. But now, I don't think if there is time for me to continue to solve this, to put the Lagrange function for this UE and then try to write down the optimality conditions. What I will probably do is I will record a video right after the class. Maybe I'll give myself a few like half an hour break, and then I'll record that video and then I'll upload it on Moodle. Okay, so you can continue watching that video after the lecture. So what I'm going to do next after we finish the class is I'm going to re-talk. I will talk again about this optimization formula, the UE optimization formula, and then I show you how you can actually try to reformat this a little bit, like bringing this xi into the objective function, so you are only left with these two constraints, where you have a linearity constraint and also a non-negativity constraint. So you can actually apply that general optimality conditions and the Lagrangian function that we reviewed to be able to solve this. So you put the Lagrangian function, you write the Lagrangian function, and then you set up the optimality conditions, you take the derivative of the Lagrange, etc., etc. So you set all these. I mean, I'm going to record this, so don't worry about this. You go over all these derivatives of the Lagrange, etc., etc., and then at the end you find you actually set up with you actually end up with UE optimality conditions. And that's the final outcome. So we set up the UE as an optimization. We apply the general optimality conditions with the Lagrangian approach to that optimization formulation that we put together for UE. And then we solve it mathematically. And then we get to these UE optimality conditions. And each of these conditions actually have a physical meaning. I will go through them in my video for you later, so you can review.